Welcome to today's demo from Introspect Technology. Today we will talk about the SV1C test system, and specifically we will describe how to generate simple electrical idle sequences using software commands. So the concept of today's demo is illustrated here. We basically want to generate periods of out-of-band bursts, signal bursts, that are interspersed into periods of long electrical idle signals. And so the key is to be able to switch from active signaling to idle signaling instantaneously, basically, based on software commands. So the waveform we will produce today is shown here as a sequence of 6 bursts as in the ComSAS requirement. In terms of timings for today's demo, we will operate at 1.5 gigabits per second. And we will generate out-of-band bursts that last 106.6 nanoseconds and ComSAS idle durations that last 960 nanoseconds, and then a negation period that's programmable up to 1,600 nanoseconds. So if we do the math at 1.5 gigabits per second, these time durations correspond to 160 unit intervals for the burst itself, 1,440 unit intervals for the idle sequence itself between bursts, and then 2,400 unit intervals for the negation period at the end. In terms of hardware, this is the setup. We will connect the SV1C tester as shown here to an oscilloscope. The SV1C has 8 pattern generators, but for the purposes of today's demo, we'll just connect one of these, channel 1 basically, to the oscilloscope with both the positive and negative terminals on it. And then we will use one other channel from the SV1C to create a trigger sequence that is time-locked to our burst pattern so that we can view it easily on the oscilloscope. So we'll go ahead and start the demo now. And so for today's demo, we have 2 windows that are active on the screen right now. We have the Introspect ESP software, which we will use to program the SV1C. And then in the background, we have a live connection to the oscilloscope connected to the SV1C so that we can see the signal behaviors as we program the system. So we'll go back to the GUI here for a second. The first thing that we do, as is the case with any SV1C test program in general, is we set the data rate using the global clock config.setup command. So here's the global clock config component, and it's able to produce any frequency, any data rate, just like any other test procedure within SV1C. For today, we will program it at 1,500 megabits per second. After setting up the data rate, we want to define basically the squelch pattern generator, the way we want to tell the test system when to go idle and when to allow the bursts to happen. So for that, we define a pattern, a squelch pattern, which is defined in exactly the same way as any other user pattern in the system. So we'll go here to the bit declaration for the squelch pattern, and we are defining it here using simple Python code. And so the code is listed here in one line. As was mentioned in the PowerPoint, we want to have bursts that last 160 bits, and so we define 160 bits of value 0 here as the burst. And then we want to go idle, and so we want to tell the sequencer program for the idle generator to send a 1, specifying that it wants to go idle, and we want that to last for 1,440 bits. And then the entire sequence we want to repeat 6 times. So this is very simple shorthand Python notation for creating long strings of 1s and 0s. We're simply concatenating 1,440 1s with 1,160 zeros to create a very long bit stream. I could have entered the bit stream one by one by hand, but this is just a very convenient shorthand notation leveraging the power of Python, the Python language. So that's the declaration for the squelch pattern generator that we have created. Next after that is a TX channel list for the scope trigger, so we won't necessarily look into that. It's basically creating a very slow pattern that is time locked to our burst. And then finally, we go to the channel that we want to produce the pattern on, which is TX channel list 1.setup. TX channel list 1 is declared here at the top, and it basically, we've declared 2 channels, although only one channel is connected to the oscilloscope. And then we've defined a pattern called out-of-band burst, which is really just the 0011 that we want to produce within the burst. So as you can see, the declaration for TX channel list 1 is like any other declaration you would do in the SV1C. So we'll go ahead now and start the program. I'll just minimize the window here as much as possible so that we see the scope. And so I'll click Run. And when I click Run, the pattern will start playing. So basically the test program has already finished. It took 1.9 seconds, and it's basically created a pattern generator. And then the waveform is shown on the scope, where we clearly see periods of burst behavior and periods of idle. I can zoom in just very briefly here to show that this is the the burst pattern being produced, and it's instantaneously moving from the idle duration to the active burst duration. So that's the basic concept of how we've created the burst pattern or the idle sequences for this particular application, the ComSAS application. For the purposes of today's demo, like I said, we connected the trigger to the scope so that we can see the signal. I'll just enable the trigger for a second. So I'll click on channel 3 here, which is the trigger signal. And so you can see it's just a slow pattern that is locked to the burst pattern so that we can really figure out what we have done. And so I've turned channel 3, which is the trigger for the scope, and I've also set up measurements on the channel. So you see that channel 3 has a high duration equal to the burst duration that I programmed. And if I look at the measurement at the bottom left here, the duration is 106.7 or approximately 106.66 nanoseconds, which we have programmed in the pattern. That's exactly the duration that we wanted. And then I've also measured the period for channel 3, which is the distance from two rising edges here, which is the entire burst duration. And you'll see that it lasts for 1066.6 nanoseconds, which is equal to the sum of 106.6 nanoseconds plus 960 of idle duration. So we've confirmed now basically that we're able to not only create burst sequences using the SV1C, but we're also able to program their timing really arbitrarily and create any kind of duration for the bursts based simply on a single Python command as shown in the demo. So before closing this demo, we'll show one other illustration for the behavior of the system, just to drive home the message that every other functionality of the SV1C is still present with this capability. So I've set up a small loop before this demo here to illustrate this, where I'm doing a voltage sweep basically on the actual burst signals, and that's usually important for testing receiver sensitivity to the out-of-band burst signal. So I've created an array variable called voltages, and it has entries from 100 millivolt to 1000 millivolt. And then I created a very simple for loop. This is just Python language. So for voltage, my current variable is called voltage in an array called voltages. I would like to, for each one of these voltage variables, I will update the TX channel list. So the TX channel list has a parameter called voltage swings. And so what I'm doing is I'm just calling this parameter, voltage swings, and I'm inserting one of these variables in it, and then performing a TX channel list one.update. And then just for the purpose of viewing on the scope, I'm putting a sleep statement here so that we can slowly see the signal change on the scope and observe the behavior as we go. So the test program is exactly as before. I just simply added this for loop here to illustrate the possibility for creating automated receiver testing, receiver voltage sensitivity testing using this paradigm. So I'll click Run just as before, and the system will start the burst and then start doing the sweep of voltage. So Run. So here's the burst. It started with a small voltage, and it's incrementing every 1 second about the voltage as it goes. So we've gone from defining an out-of-band burst signal with electrical idle signaling interspersed inside it, and then we've shown how we could control timing of that signal using very simple pattern commands, as in this command here. And then finally, we've shown that the original looping capabilities are all still available in the Introspect system. Thank you.